Does anyone have a question left over from before the break? Okay, so we are going to learn about one more kind of energy today, and that will be the final form of energy that we talk about in this unit. Okay, we will later at the end of the semester we'll be talking about thermal energy, heat energy, and in the second semester, for some of you perhaps, either we or you might in your other class if you take it elsewhere, we'll talk about electrical energy. But for now, there's one situation we haven't really been able to talk about, and this is called elastic potential energy. And we're going to use as our basic case for this a spring, but it would really, anything that's kind of stretchy, that when it is deformed, it wants to snap back into its original shape or configuration, would have the same type of potential energy. So that would be, you know, a rubber band or a bow and arrow, things like that. But we take as our basic idea the spring. So springs have a force profile that's a little different from anything else we've seen. The force from a spring is proportional to the length of the spring. So that is, or rather the length than saying length, I should say how much it has changed its length from its natural length. So this is the displacement from the natural length. And again, I'm getting really bad lag on my screen, which is at least 50% of the reason that this is hard to read. Let me try to do it again. The displacement from the natural length. So in other words, a spring normally has a certain length, and if we try to stretch it, it wants to return to its original length. If we try to compress it, it also wants to spring back. So you can imagine maybe, I'm going to do this all horizontally so we don't have to worry about gravity, but here is a spring, and maybe we connect it to a little platform, and then we could put a ball in front of the form. Then if we compress the spring, so we push it tight, and if we release it, it wants to return to its natural length, and in the process it's going to push the ball, and if we're lucky, the ball can go up a ramp and give us points on a pinball game or something like that. Raise your hand if you ever played pinball. Okay, good. So you know what I'm talking about. So the idea is the spring already has a certain natural length. It just wants to sit there. And if we compress it, it's going to try to spring back. And so we're going to think of this as being related to a form of potential energy, even though we know what really happens is the spring force is going to do work. But because the spring force is proportional to x, so what is x in my picture? We might have, this being x equals 0 would be the equilibrium position or the natural length. And then when we stretch this back, it may go to x equals, minus 10 centimeters or something. And so the force is proportional to that. If we make it stretched back a distance of 20 centimeters from the starting point, the force will be twice as big as if it's at 10 centimeters. So the way we write this is we say that it's equal to minus kx, where x we already defined, and the k is known as the spring constant. Now this expression is known as Hooke's law. I've always been a little jealous of Mr. Hooke because this literally, if we were in class, I could prove this law to you in like 5 minutes with a spring and a couple 100-gram masses. But at any rate, it pays to be the first to do something. So Robert Hooke was incidentally the teacher of Isaac Newton, who introduced Newton to the idea of gravity and was really, really mad when Newton figured it out before him. So he gets Hooke's law and no one knows about him, and Isaac Newton gets to be sort of the father of physics. Okay, so now here's the problem, why I haven't talked about spring forces yet. Because this force is not constant, the acceleration of something being pushed by a spring is also not constant. And as we know, our master equations at the beginning of the semester only work for constant accelerations, and therefore for constant forces. This is not a constant force. So how about energy? Will energy work? Well, it's tricky, because remember, we have work. Our definition is force times delta x times, cosine of theta. In this case, there's no real need to worry about the angle, because the force, pushes to the right, and as this thing pushes the ball, the delta x also points to the right. So we're going to have cosine of 0 in the particular picture that I'm looking at here. But the problem is, how do I know what value of force to put in? Because when x equals 0, there's no force at all. And when x equals 1 centimeter, there's a little bit of force, but not much. At 2 centimeters, there's more. There's a lot of force at 10 centimeters. So, the value of force that we would put into this equation becomes ambiguous, even though we know that it travels, in this case, 10 centimeters. So here's an idea what we could do. And I'm going to graph the force versus x to give us a sense. So if I graph that, I get a straight line. This would be the spring force. Okay. I get a straight line with a negative slope because of that negative sign, and the slope is then just minus k. Okay, so this is a, kind of like y equals minus kx. Instead of y, though, it's fs. But the constant in front of the x is the slope. So what we could do, if we wanted to find the work done, is we could find the force at 1 centimeter and at 2 centimeters and so on, all the way out to 10 centimeters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 centimeters. And we figure out what the force is at 10 centimeters. That would be illustrated right here. I'll tell you what I'm going to do. I'm going to blow this whole thing up so we can really look at it. Really, I just want to look. Come on. I got to figure out why this lags so much. Okay, so what we do is we find the force at 1 centimeter, and we assume that that force is the same the whole time. And we compute the work that the spring does over the course of that 1 centimeter. And the work would then be, could be illustrated by just the area underneath that curve. And I would be overestimating it a little bit. Then we go ahead and we find at 2 centimeters what the force is. And for the next centimeter, we imagine that the force is a constant. Let's see if I can fill this in too. And then the work would be the area, because remember, work will be force times displacement. So we can think of this as kind of a delta x1, and then a delta x2, and this would be force 1 and force 2. And we would say the work would be, force 1 times delta x1 plus force 2 times delta x2, and so on, all the way up to force 10 times delta x10. So if I want to do that, then pictorially, what it looks like is I'm finding the area of a bunch of rectangles. So I'm done drawing the rectangles, but it's kind of catching up with me. So then to find the area of these guys, I knew that was going to happen. Okay, I can't get that last one filled in for some reason. Maybe I can get it. Anyway, the idea, now that I illustrated this, the idea is that if the force is changing, I can pick small little movements and treat the force like it's roughly constant during that small movement, because it doesn't change too much during that small movement. And if I add up the work from, let's say, each centimeter, what I get would be this blue area, the sum of all those rectangles. And we're overestimating the work a little bit, because essentially the top little corners here are over my line, and so any place over my line, I'm estimating a little too high the work. But I could do it on millimeters instead of centimeters, and then I would have more of these little corners, but they would be very small. Or instead of millimeters, we could do micrometers or nanometers. And basically the final punchline is that in the limit, that we split it up into nanometers, into picometers, into the smallest little movements possible. The area of our shape really reduces to just the area underneath, or in this case, on top of my graph. So if I come back here to this picture, then let's say we wanted to go from 10 centimeters to 0, like what I've illustrated in that picture, we could just find the area, and that would be our representation of the work. Does anyone know what this process is called? This process has a special name. So the process is known as Calc 2, or it's actually called an integral. Now, we're not going to find integrals. Integrals are how you find areas under curves. In our case, it's really easy because this is just a triangle. And we know how to find the area of a triangle. So we don't actually need Calc 2 or any fancy mathematics to do this. We just need this concept that if I want to find the work done by the spring to move from a point A to a point B, then I just need to find the area underneath this graph, or in this case, it would be above the line, between the line and the x-axis. Okay, any questions about that concept? Ziad.
So we just need to find the area of the triangle?
Yeah, so the work equals the area. That's right. So let's see how it works in practice. Okay, let's do a particular example. Suppose I have a spring. So the philosophy is as follows: network equals change in energy, and the network is going to be the work done by gravity now plus the work done by the spring plus the work done by other forces. And this should be delta KE technically. Then we take these guys and we move them to the other side. So we have the work done by the other forces equals delta KE plus delta PE for gravity, and then we have minus the work done by the spring. Okay, minus the work done by the spring. So we're going to try to compute a generic formula for work done by a spring if we go from some x initial to some x final. So the idea is we want to find the area of this shape. So how do we find the area of that shape? It's not actually a triangle. Well, it's pretty easy actually, because what we can think of, I didn't mean to do that. What we can think of is that there is a large triangle. So I'm doing a large triangle in red. And then there is a small triangle, which I'm doing in green. If you can't see red and green very well, just there's a large triangle going around the exterior and a small triangle there. And the idea is the area I want is the area of the big triangle minus the area of the small triangle. So the work from the spring would be the area of the big triangle minus the area of the small triangle. So that's 1/2 base times height for the big triangle minus 1/2 base times height for the small triangle. So what's the base? The base is the length of this, which in the case of the big triangle is just x final. So that's 1/2 x final, and we'll figure out the height in a minute, minus 1/2. The base of the small triangle it's just x initial. 1/2 x initial times whatever is the height of the small triangle. So remember, the vertical axis is the force. So the height of the triangle would be the force when it's at this location. And so the force when we're at x initial would be minus k x initial. And the force when we're at x final will be minus k x final, just using the force law for springs, Hooke's law. So we have minus x initial and minus x final. Sorry, I did that backwards. For the large triangle, we got minus k x final. And for the small triangle, it's minus k x initial. So simplifying a little bit, we have x final times x final, so this gives me minus 1/2 k x final squared plus 1/2 k x initial squared. If I factor out a minus sign, which I know that's kind of a weird thing to do, but if I factor out a minus sign, I get 1/2 k x final squared minus 1/2 k x initial squared. And now, why did I factor out a minus sign? Because this now looks like a delta. So we get the work done by the spring equals minus delta of a quantity, 1/2 k x squared. So in analogy with what we did for gravitational potential energy, where we found that it's always equal to a delta something, we will call this delta PE spring, or I guess the delta's on the outside. So the quantity inside the parentheses, we call that the potential energy minus the potential energy of the spring. So let me just put this back into our equation so we can see what we have. We have work done by other forces equals delta KE plus delta PE gravity minus a minus delta 1/2 k x squared. Those two minuses cancel. This is exactly what happened with gravity. And then we call that guy spring potential energy. So let me pause. The idea here, what we did is we saw that because the force of the spring is not constant, to find the work done by the spring, we have to find areas. And to go from x initial to x final would mean finding the area of this shape. When we did that, we saw that the area really looks kind of like a delta of something. And that's what allows us to play this game where we treat it like a potential energy. So going forward, if we have a spring in our problem, we're going to say network equals change in energy. But that's going to change in general into, it's going to split into delta KE plus delta PE. And now we put a little g to remind ourselves that that's the potential energy due to gravity plus the change in potential energy for a spring. And we keep in mind that this work on the left is all the other forces other than gravity and springs, but we don't always write that. We don't always write other forces. And we have an expression for the potential energy of a spring, which is just 1/2 times the spring constant times x squared, where x is how far the spring has been stretched or compressed from its equilibrium length. Okay, any questions? Okay, I think this will probably be clear as we put it into context with the problem. So let's go back to that initial spring that we had, where we had a spring and a platform and a ball, and that spring has been compressed to x initial equals minus 10 centimeters. And it's minus because it's to the left. And we can think of it as the spring is compressed, it gets minus length, and as it becomes stretched, it gets a positive length. And we release this from rest. And we're going to find B final for a 100 gram ball if K equals 100 newtons per meter. So that's a typical unit for spring constant K, newtons per meter. And so we look at this situation and we say to ourselves, I have no idea how to find the acceleration of this thing because the force isn't constant. But I can think of the spring as having potential energy. And so we say that the network equals the change in the energy. And if there's no friction, there's no network. So change in energy is just change in kinetic energy plus change in gravitational potential energy plus change in now spring potential energy. Of course, if in a particular problem, it's not going to go up or downhill like this problem, we can cross out the change in potential energy due to gravity, or maybe not even write it if we are thinking ahead. And likewise, if there's no spring in our problem, there's no need to write delta PE spring. And then we just follow the same logic. So it's a new force, it's a new energy, but the logic is the same. We have KE final minus KE initial plus PE spring final minus PE spring initial. And we go through these one by one and ask, do we have them? Do they exist in this problem? Is there final kinetic energy of this ball? Yes, because like a pinball game, when I release the spring, this platform, it goes back to equilibrium, and it just kind of goes boing and kind of stops there, but the ball keeps going. So it's going to have kinetic energy. But did it have initial kinetic energy? No, not if I release it from rest. Now, how about spring potential energy? It definitely initially had spring potential energy. What about at the end? Well, the quick answer is no. The long answer is, in real world physics, the spring does keep some energy because it kind of goes back and forth. But when we're reading physics problems, they always say a massless spring. And if it's a massless spring, it's like it just stops instantly at x equals 0, and there's no more potential energy. So in textbook problems, I would say there's no final spring potential energy. But in real life, there would be some of the energy would stay in that spring. And then we just rearrange, and we're trying to solve for final velocity, so we want to get KE final on the side by itself. Technically, I'm moving the minus PE spring initial to the other side, and when I do, it becomes positive. But then I'm flipping sides so that the thing I'm solving for is on the left. This gives me 1/2 mB final squared equals 1/2 kx initial squared. And now, like virtually always with these energy problems, the algebra is just really simple, moving stuff from one side of the equation to the other and canceling things. So I can see the 1/2s cancel, I'm going to divide both sides by m so that we get v final squared by itself. We have k x initial squared over m, and that means v final is the square root of k x initial squared over m. Now units will hit you here if you're not careful. So the k has newtons and meters. Those are base metric units. But my x initial is in centimeters. So I have to make that meters. So negative 10 centimeters is the same as negative 0.1 meters. And then we square it. Because we square it, it doesn't matter if it was negative 10 or positive 10. And it never will. And then we divide by the mass, which is 100 grams, but I have to convert that into kilograms, or else my units are going to be all messed up. So that gives me 31.6. meters per second. Okay, any questions? So the logic is really exactly the same. It's just we now have a new kind of potential energy. So as you're studying and preparing for this contest, there's basically three things that you intuitively have to really get. You have to know intuitively, when do I have kinetic energy? You have to know, when do I have gravitational potential energy? So we have kinetic energy if the object is moving. We have gravitational potential energy if the object is not sitting at height 0, which we get to choose where that is. And then we have to internalize and know, when do we have spring potential energy? And we have spring potential energy as long as the spring is not at its equilibrium length. So if it is stretched or compressed by any amount, there will be spring potential energy. If you can get the logic down to those and be 100% confident on those, then the process will solve the problem for you with very little thought on your end. Just follow the process. So let's do another problem, unless there are questions. Any questions? Ziad?
When did we have spring potential energy? That's only if it's stretched.
Yeah, so it comes from this x in the formula, where x is the length of the spring relative to its natural length. So if we stretch it so that x is not 0, then we will have spring potential energy. If we compress it so that x becomes a negative number, then we still have spring potential energy. So as long as the spring, if it's at its natural length, then there's no potential energy. But if it's not at its natural length, then there is spring potential energy. And that kind of comes out when x either equals 0 at the natural length or doesn't equal 0. Okay, Haley?
Okay, whenever we're solving and you went from like the potential energy of the spring and then the k x initial, so the k in this case is the kx is a spring constant, not kinetic energy, correct?
Yes, it's a lowercase k
Okay.
versus a capital K. Yeah, and then the capital K, we never just see K, we see KE.
Okay.
KE is one thing. Yeah, that's a good thing to point out, and it's going to happen more and more for us as we go further in the semester. We find that we use T already for tension and for time and for period of orbits, and there will be other uses for many of our symbols. So that's definitely a tricky thing. Okay, other questions? Haley, again?
No, I'm sorry, that was an accident.
Okay. All right, so let's do another problem with the spring. So suppose we have a spring and it's compressed, and it's going to push a box this time. The x initial, let's say it is minus 15 centimeters, and the k is 1,000 newtons per meter. And the mass of the box is 1 kilogram. And we're going to push it, we're going to release it and let the spring push it and so that it slides along the ground and then up a ramp. And I want to know what is the maximum height it achieves. Okay, how high does it go? So we have network equals change in energy. Now, this one, there's multiple ways to solve this. What I recommend is we notate the initial position and what's the final position kind of from the beginning, so that as we're going through what do we have and when do we have it, we know where initial and where final is. And if there's no friction, so let's just say there's no friction, mu equals 0, then there's going to be no work. So this would be another, what I would typically call a conservation of energy problem. So since the energy is conserved, philosophically, we're starting some spring potential energy, and at the end, we're going to have some gravitational potential energy, and in the middle, we have kinetic energy. So we would have delta KE plus delta PE for gravity plus delta PE for the spring. You know, it's probably good sometimes that this lags when I'm writing because that gives you time to copy. That's something I didn't think of. That's probably useful. Now, I want to look at all three of these deltas and make sure that they're appropriate for this problem. So, does the spring potential energy change? Yes, it will, because the spring is compressed initially, but by the time the box gets up here, the spring will no longer be compressed. So we definitely will have a change in the spring potential energy. How about gravitational potential energy? Does that change? Well, initially we start at one level, and at the end we're at a different level. So no matter what I call y equals 0, the y value changes. So I definitely have a change in gravitational potential energy. How about kinetic energy? What's my velocity at the beginning? Anybody know the velocity at the beginning? Dustin?
0.
Yeah, it's 0. And what's the velocity at the end?
It'd be 0 as well when it stops, right?
Exactly. So therefore, I don't need change in kinetic energy because the initial kinetic energy is 0 and the final kinetic energy is 0, and I can just cross this out now. I don't have to cross it out now if I don't realize that it crosses out, but if I do realize it, it's going to save me time. So let's cross it out. That is not 100% intuitive, I know, because the kinetic energy is changing the whole time, but all I care is from beginning to end. It doesn't matter that it's moving in the middle. It started at rest, it ended at rest, so if I would actually put in 1/2 mv initial squared, I'm going to get 0. And if I put in 1/2 mv final squared, I'm also going to get 0. So we might as well cross this thing out now once we realize it. So we're going to have 0 equals PEG final minus PEG initial plus PE spring final minus PE spring initial. Some students solving this problem would want to do the following. They would want to find out how fast this thing is going after the spring releases it, which would kind of look like doing this. And then part 2, say now it has kinetic energy and it's turning into potential. So you do it that way, but there's no need to stop the problem in the middle and find how fast is it going in the middle. Now we go through all of our terms one by one and see, do we have it? So for potential energy, again, I think it's a good idea to just draw a line wherever we want to be y equals 0. And then this number here will become what we call H max. So if that's my 0 line, then we definitely do have final potential energy, but we definitely do not have initial potential energy. Now we do the same thing with the spring. Do we have final spring potential energy? So when the box gets here, is the spring still compressed? The answer is no, not still compressed. Ziad?
I just wanted to ask, we're asking if the box is not compressed?
We're asking about the spring. Is the spring still compressed? Because
okay.
the spring is what stores the spring potential energy.
Of course. Okay, I got it. Thank you.
Okay. Was the spring compressed at the beginning? Yes, it was. So I cannot cross that out. So we're going to have those two. Okay, good. So now we rearrange and we figure out what we're looking for. I know now that PE gravity final equals PE spring initial. And again, the more you practice this, the more conceptually you might understand this from the beginning. That because there's no friction, that this must be true. And you could just jump right to here if you're really getting that concept. And I'm looking for H max. That's going to be inside of the gravitational potential energy. So let's write that formula. It's going to be M times G times Y final. And on the left, we're going to have 1/2 K X initial squared. My Y final then is going to be K X initial squared over 2 mg. And that's my H max. So we can plug in our numbers. We're going to have 1,000 times minus 0.15. Again, I have to convert these into meters. I guarantee you, if you feel like you're doing everything right and you're getting the wrong answer, that there's a very good chance you just need to look at your units. And then we have 2, and the mass is already in kilograms, so I don't need to convert it. And G is already in metric units when I use 9.8. So let's see what we get. I get H max equals 1.07 meters. Okay, Haley.
I was just wondering if the YF isn't squared, why do we have to take the square root for the answer?
That's a really good question. Justin, is that what you were wondering too?
Yes, sir.
Yes, I'm just tired or something. We shouldn't take the square root. You're 100% correct. So we'll see if I square that again. What do I get? 1.15. Apologies. Absolutely right. We do not take a square root here.
I have another question.
Haley, yeah.
So whenever we're writing this down, and we're doing like the sum of the work of all the forces, is there like, why do we not have to draw in the forces for the box and we're only like worried about the spring?
So are you talking about for this picture here?
Yeah.
No. So the box is sort of our system. Okay, the box is the system, and the spring, like gravity, those are forces that act on the box. So if I would draw forces on the box, so we're talking about the box, that's the thing that's changing, that's going from point A to point B. We're going to have the spring force and the force of gravity and normal force. And there could be friction too. And so the forces on the box are what we're considering when we do the network. But we don't consider the force of the spring as doing work because instead we now have potential energy for springs. And that's a lot easier than drawing a picture every time and finding area. And that's kind of why we do it. We don't consider the force of gravity as doing work because, again, we have a formula for potential energy due to gravity. And that's easier than having to draw the force of gravity and find the cosine, the theta, g, and do that whole process. Normal force, we could consider it. If we're on an elevator accelerating upward, then the normal force is doing work because the normal force points in the same direction as the motion. But if we're sliding along the ground, the normal force makes a right angle, and that's when it doesn't do work. And the friction would do work if there were friction in this problem. Okay, so yeah, you don't really think of the spring as part of your system. You think of it as something kind of acting on your system. Good. Any other questions? Okay, let's try, we've got a little time left. Let's try one more problem with a spring from the book. So this is 3,000 problems. Problem number 7.107. It says, as shown in the figure, a block of mass m is resting on a horizontal surface. So the figure looks kind of like this with a spring between some kind of wall and the block. So the block has a mass m, spring has a constant k. And it says it is resting. The coefficients of static and kinetic friction are given as mu s and mu k, respectively. The block is attached to a spring of negligible mass, having spring constant k. Initially, the block is at rest, and the spring is relaxed. So this tells me x initial equals 0, and b initial equals 0. Then the block is struck sharply so that it begins to move to the right with speed v0. So actually, they're really starting it after we strike the block and saying that's now an initial velocity. How far does the spring extend before the rightward motion is arrested? Okay, so what happens is we have it in this situation, and then all of a sudden someone just pops it. And I'm going to call it VI instead of VO because that's kind of what we've been using. And just to stay consistent with that notation. And we want to know how far does this thing go before it stops. So that means the final equals 0. Okay, and we have a coefficient of friction, mu k, so we have to kind of keep that in mind. Now we're going to get, since we don't have numbers, we're going to get just a formula. Okay, what are we looking for exactly? We're looking for x final. What is the final position of this thing? Okay, so we've translated it. Now we go to our equation, which again, we have only one equation. How awesome is that to always know where you're starting? Okay, it's kind of like how you can navigate to places a lot better from your house because you know you start there a lot, and so it's easy to find your way. Okay, so net work equals delta KE. Is there going to be net work? Yes, because there's friction, so that's going to be the work done by friction. The delta E will be a delta KE potentially plus a delta PE gravity potentially plus a delta PE spring potentially. But as we think about this, we'll realize that you know, there's no change in potential energy due to gravity because this is on a horizontal surface, so it does not change its height. How about kinetic energy? Well, it starts with, you know, some number for V initial, and then it goes to 0. So they're kind of treating this problem as beginning once this thing has gained its initial velocity. So we do have a change in kinetic energy. And how about the spring? Well, it starts off relaxed, and then it's going to be stretched at the end. So yes, we have that. Now in the picture, maybe to draw this, where, you know, where is it going to be? It's going to move some distance, delta x. So if this is x initial, this is x final. We just want to know x final. Now the work done by friction is going to be friction times delta x times cosine of theta friction. And that's going to be equal to KE final minus KE initial plus PE spring final minus PE spring initial. I'm hoping you can see why I've been insisting we work with symbols, you know, that you practice with symbols, because this is all symbols. You know, we don't want to be relying on just plugging numbers in, because we want to think symbolically. I want to be able to look at all these symbols and say, hey, there's no final kinetic energy, so I'm just going to cross that out. And there's no initial spring potential energy because it said x initial equals 0. Let's see, my frictional force would be mu kinetic times m times g. And delta x is x final minus x initial. And theta f is 180 degrees. And then minus 1/2 m v initial squared plus 1/2 k x final squared. So all symbols. What can I do with this? Well, the cosine of 180 is -1, and I know x initial is 0. So I can simplify a little bit. We have mu k mg x final and a minus sign in front because of that cosine of 180 equals -1/2 m v initial squared plus 1/2 k x final squared. Now, all symbols, right? What we want to do is we want to solve this for x final. So we have to kind of think what is given. And that's, no numbers are given, but they refer to numbers. They say a spring constant k and a mass m. So we should think of it as if we know k and we know m. They say it's given an initial velocity vi, so we think of that as known. We know 1/2. We know g. They say there's a coefficient of friction mu sub k. And so basically everything in this equation is given other than the x final. So how do we solve such a beast for x final? I have something times x final equals something plus something times x final squared. How do I get x final alone? Ziad.
The quadratic formula?
Exactly. This is a quadratic equation. So to do that, we have to put everything on one side. That's going to look like 0, but it's not going to look like it in red. It's going to look like 0 equals 1/2 k x final squared plus mu sub k mg x final minus 1/2 m v initial squared. And then we identify the 1/2 k as our quote-unquote a in the quadratic formula, and the mu kmg as our b, and the minus 1/2 m d initial squared as our c. So x final is going to be minus our b. Now this is a terrible, ugly, nasty looking thing, but if you have gotten comfortable working with symbols, this is not a hard task. This is just, it looks bad, but it's not bad. It's kind of like chili, maybe. Maybe chili, I don't know. Chili when I was a kid, it looked bad, but it tasted good. Now it just looks good because I know I like it. But you can think of your own dish that fits that. Cat.
Oh, how do we know that 1/2 k x final squared is a? Could we also use, like, we put a c as a since it's also squared?
No, because that's a great question though. Because the variable is x final. So wherever the x final squared is, that's where the a is. Just this v initial squared is not part of, that's still just some number.
Okay, that makes sense.
Does that make sense? Okay. Yeah, that's the thing. It's when we're working with symbols only, it's tricky, and that's why I like to use colors to underline stuff to sort of draw my eye to what is my variable. What's the variable? So it's the x final. Okay, so then we have minus b plus or minus the square root of b squared. So we're going to put our b, which is mu k mg, in there and square it, minus 4 times the 1/2 k times my c, which is minus 1/2 m b initial squared. All of that over 2 times 1/2 k. And I can't really simplify this too much, but we can simplify a little bit. Like when we see a 2 times a 1/2, we can cancel that. And when we have a 4 times a 1/2 times another 1/2, those guys are going to cancel. And I have 2 minus signs inside, and those will cancel. So the final expression is minus mu k mg. This k should be really a subscript here. So mu sub k mg plus or minus the square root of mu sub k mg, that whole thing squared, plus mk the initial squared all over k. So it's ugly, it's messy looking, it's ugly if you're not into math symbols, I guess. But the individual steps follow a certain logic, okay? Again, if you haven't been working with symbols, this looks like overwhelming. But if you're working with symbols, you can solve a problem like this just by following it systematically. And probably the trickiest part is what Kat asked, you know, how do I identify the A, the B, and the C? And that comes back to knowing exactly what's your variable and what are the other things which you can think of as all constants. Okay, any questions about this problem? Other questions? Okay, well, that concludes our unit on energy. So you now should continue practicing your homework, and you know, come back tomorrow with questions about, you know, homework. Maybe arrange to stick around after class and ask questions, or come before class, or set up a time and collaborate to meet with me if you've been doing problems and are stuck on some things and need some help. You do have a lab that is due tomorrow. Like the last lab, it's fairly short. It's more just an exploration to kind of give you some visual, you know, cues that help make sense of all of this. And then we have our contest on Friday. Any last questions for me? Okay, then I will see you next time. Thanks a lot.